Hi, today we're going to talk about Delaunay Triangulation. So it is a method for basically, since we are doing FEM simulations, we want to discretize domain, and Delaunay Triangulation is a method which splits computational domain, again if we talk about FEM, into triangles. And Delaunay is just a specific algorithm that provides some criteria how to do it and how to get a well-behaved mesh. So much of my presentation here is inspired by this particular book. It is an amazing book. I absolutely recommend if you're interested in things like interpolation, if it's relevant for you. Like if it was my kind of priority topic, I would enjoy it, I would study it thoroughly. So yeah, this is amazing book, resource. They have video resources. I strongly recommend it. But they discuss kind of from perspective of terrain modeling, and so the main theme of this book is ways to interpolate data. And we will also kind of start from this idea, although we will start from something as simple as one dimension. And so I can give you, for example, task. I give you a bunch of measurements at some specific points, right? And then I can ask you, okay, what do you expect the value to be here in the between 2 and 3 or something, or anything similar. So in one dimensional, it's kind of trivial. What you can expect that you have to grab these points, kind of edge nodes, and then do some kind of calculation to retrieve value here. So of course, in one dimension, it's very, very trivial. You just have to understand in which interval this point of question lies, and then you do something with these values on nodes. And so yeah, in one dimension, okay, what you would do, of course, maybe you will sort them, and then you will go through each element and say, okay, whether point is in this element. And anyway, it's kind of easy, but next question would be like, what you actually would do with this kind of node values and neighboring node values. And maybe you can take left, just say in this particular interval, we will just assign the value of this left node or right node. Maybe you can do something like some average between nodes. Maybe you do something a bit smarter and you do linear interpolation. So it's kind of a weighted sum from a distance from both nodes, right? So there's kind of not a big problem. You don't have to think about this kind of splitting our kind of mesh into elements. It's very, very trivial. But when we extend it to 2 dimensions, so in this case we have to partition our domain into areas. And in this case, the simplest area we can do is triangle. It requires only 3 points. But then if I supply you our kind of measurement coordinates, there are, I'm not sure about infinitely many, but there are many ways to actually split this area, split this domain, partition this domain. And for example, left and right hand side, maybe what you can see is that left one is kind of more uniform, while the right triangulation, it includes some kind of stretched elements. And having a stretch elements is kind of bad. Well, I don't know how to properly explain it, but for example, we want our nodes, because we're dealing with we're doing some math with node values. It would be best if these nodes were describing some local neighborhood. So in a sense, we want distance between these nodes be minimal. Yeah, and maybe you can express it in terms of angles. interrelate this stuff. But yeah, for example, I say I want to interpolate, so I want to ask a value at this particular point. And then I will use these nodes to actually calculate something. It will be kind of, maybe it will be weighted average something of these nodes or something. And then if we take a look at the same point somewhere here, if we again apply this kind of weighted averaging, these nodes are very far away. They don't describe this neighborhood very well. In fact, there may be a lot of kind of variation of what we're measuring underneath, and we will not include it. So that's why kind of having a stretched element is a bad idea. And here's an example from the book. The bottom is our partitioning, so it consists of some triangles, and the right part, it is partitioned using Delaunay Triangulation. And their results are staggering. When we have these kind of long elements, we linearly interpolate, and we are completely missing whatever happens underneath. So it's a very nice example. So actually, how you partition this domain matters a lot in your output, the quality of your interpolation. An example that I will give you now, for example, okay, if we have this bad mesh, like how do we fix it? Can we go from this mesh from right to the left? And then we make this kind of observation that two triangles form a quad, and this quad can have two diagonals, one of two diagonals. And based on which diagonal you choose, you will get, for example, here one thin triangle and one kind of okayish. Or if we choose this blue diagonal, we will create two okayish triangles. And the observation is also that by flipping, because this operation of changing diagonal is called the flip, kind of by performing this flip, we don't change anything in surrounding triangles. So it's a local procedure. And so let's try to maybe do it manually. Just an example. Okay, obviously we see it would be nice to remove this long diagonal, and this diagonal, let's make it a bit more beautiful. Let's erase them. In just a second. Yeah, and let's introduce new diagonals. Also, what we can observe is maybe we can remove this and swap diagonal. What else can we see? Maybe we can perform this flip here. And maybe here. Okay, it looks a lot better. I don't even see what else can we improve. So, and what I propose is that we compare it to our original. I said compare it. Okay, we will just move it. So as you can see, we kind of recreated the original triangulation. In fact, we even swapped this edge and we kind of improved it. So what we just did is we kind of discovered some kind of method of making triangulation better by flipping diagonal, and how to kind of do it quantitatively. So this is called a Delaunay kind of condition. So we can, using this condition, check whether we should flip or should not flip. So when this condition is such that we take one triangle using some diagonal. We inscribe it, if it's correct word. Anyway, we create this circumcircle. It's a circle that in which all the triangle vertices live on circumference. And then we have our diagonal, and we check whether the point of this kind of adjacent triangle, this node, whether it lies inside this circumcircle or does not. In this case, when we're using this green diagonal and this triangle, we see that this point kind of fails this criteria, and it lives inside of our circumcircle. We could have inscribed this triangle, but then we would create this kind of huge circle. It's really big. And then we would check whether this opposite node is inside. And of course it will be inside. So, and if this condition fails, we just flip the diagonal. And here, for example, we consider blue triangle with blue diagonal. Again, we do this circumcircle, and then we kind of, in this direction, we check node which is adjacent, opposite to this edge diagonal, and we see it's inside. So kind of using this criteria we created, it shows that we have improved our triangulation. So the full, it's only a part of a true algorithm, and our true algorithm would be similar to what we discussed in previous video on when we kind of split one-dimensional mesh by inserting points, which was kind of looked very trivial at that point, but it kind of shows you the introduction into this procedure into dimensions. So yeah, this particular circumcircle test is only one part of this algorithm, of course. And if you're interested how to do it, we just supply vertices of our triangle, we supply some kind of point, and then we create these two matrices, matrix and vector, and then we solve for these coefficients, and from it we retrieve the circle parameters. So in Godot, you have to do it like this. First of all, you have to have linear algebra package add-on, whatever it's called, extension, which is free. And then you have to create kind of this two matrices, matrix and vector. In this case, I do it row by row, and then we kind of invert, solve for this ABC and reconstruct our coefficients. The derivation is about like this from ChatGPT, which kind of made mistakes. Okay. So yeah, we have discussed kind of how to do this circumcircle test, but actually, of course, what we did is that we started with actually existing mesh. In real life, you will not have mesh; you will have to create it. So in this process of creation will be about splitting triangles into more triangles. Similarly, like we did in one-dimensional case when we split one interval into smaller intervals. To begin with, we will create this kind of master triangle in which we will start to insert points and splitting it into many triangles. And then we insert next point and we will split that triangle. And in the end, we will just strip all the kind of useless, unimportant triangles, and we will only get the triangulation inside, which is important for us. So yeah, but in order to actually start splitting, you have to know which triangle you have to split. And so we will discuss this point kind of procedure. So actually, it's not an easy procedure. We will not now kind of delve into like multi-layer problem when we will we're trying to solve this particular, how to find a point in a triangle, and then we will realize, okay, we need this, this, and this. So it will not be as fast. But the question is, how do you find whether the point is inside the triangle? How do you do it? Like, what is the algorithm? So maybe how I would transition from nothing into like working algorithm, I would like to introduce this particular idea that we have to understand. We can introduce, like, from a kind of geometric or set theory approach, we can introduce three half planes, which are kind of based on triangle edges. And then we realize that the triangle is nothing else than intersection of these three half planes. And to check whether some kind of point in here, for example, I've drawn 6 points, whether it is inside the triangle, it has to satisfy kind of this three checks, whether the point is, I will call this kind of positive half plane or something, whether it satisfies this kind of question, whether it's on this positive half plane 1, half plane positive on half plane 2, blah blah blah. So for example, this point, it is kind of green, so it satisfies all three conditions. So we say yes, it is inside of triangle. But then some other point, it satisfies only one check but fails two other checks. And this kind of half plane approach, it's only an intermediate step. It's like an analogy in our case. What we can think about, maybe if we can introduce like for each half plane coordinate system, like local coordinate system, and this system will be based on this orange, I will call it tangential vector, but it's our edge vector, and then we will need kind of orthogonal vector, which I will call normal vector, and we do it for all the edges. And when it comes to performing this check whether the point is on this kind of positive half plane or not, from this kind of local coordinate system, we will draw a vector into our point, and then we kind of decompose it into normal and tangential components. But in fact, we only need kind of this component in this direction. So we only need to know normal direction of normal vector. And also the position of this local coordinate system, we don't really care as long as it's somewhere here on this line. Because again, we only care about normal component, and by translating this coordinate system along this line, we will change only x component, which is not important for us. So in this example, we see that this point and the vector that is created from origin to the point has positive projection onto normal, and the point outside the triangle has negative. So that's what we will seek. Now the question is, yes, we have this kind of tangential vector, which is simply maybe normalized edge from vertex 1 to vertex 2 or something. How do we get this normal? And kind of it looks like it's enough to just rotate it counterclockwise by 90 degrees. So mathematically, it's absolutely the correct answer. But then we have kind of this issue. Okay, this edge, what we're talking about, it may belong to two triangles. And just by obtaining this normal vector, so obviously the neighboring triangle should have like normal in opposite direction. So just long story short, we can observe that if we flip this edge direction, then our kind of weird approach with just rotating it 90 degrees counterclockwise will still work. And it kind of introduces one of fundamental requirements is given our nodes and triangles, how do we store these edges so we can so we can retrieve this normal direction. And the idea is that we store, given again three vertices, we store edges in counterclockwise orientation. And for example, if we constructed these orange vectors or these red vectors, we see that it actually creates this effect of having opposite edge directions for neighboring triangles. How I prefer to think about it, not as some kind of rotation stuff, but actually by introducing this kind of true coordinate system, true orthonormal coordinate system. So when our tangential and normal are coplanar, and we add another dimension that's orthogonal to both of them, we will call it direction z. And so we have this expression for orthonormal coordinate systems using cross products that we can retrieve basically basis vector by cross producting to other basis vector. And then we just agree that this blue kind of additional dimension is z, that we agree on its direction. We know our tangential, which is normalized edge. And then by performing this kind of permutation, we can also find this normal vector by cross-producting this z direction with our edge direction. And it absolutely, of course, works for our neighboring triangle just by understanding how cross-product works. We can see that it works. Yeah, so maybe the implementation. So it's curious, as I said, rotation. These two approaches are actually equivalent. So in this case, if we consider it as two-dimensional problem, we take the rotation matrix, place the 90 degrees inside, and we get this particular matrix. And then we can retrieve arbitrary normal for this arbitrary edge direction, just by matrix multiplication, of course, and we get this solution, minus y, x. If we perform this operation on using our cross product, I really hate this approach of calculating cross products, but yeah, anyway, some kind of sum of minor determinants or something, I don't remember how it was called, but yeah, what we see is that we get exactly the same result as in rotation. So they are actually equivalent, except here we had to add like additional dimension. But as we will notice, we don't really need, we can just take a z kind of component, since anyway, we will see it later. And so the implementation of this procedure is as follows. We have this kind of normal vector retrieval using our expression, which is very simple. For some reason, I've called it anti-normal, and then I reversed its direction. But then when I calculated h normal, I again reversed direction. Don't ask me. I just found it hilarious that at some point when I programmed, I did it. But yeah, so again, we create this tangent direction by using first vertex and second vertex. We rotate it 90 degrees in a sense using this procedure, which is very simple. We create from origin, from this local origin, which is our vertex 1 vector, to this point, and then we just use a dot product as a projection. Of course, this normal direction should be normalized, so we get like a proper correct projection. So yeah, that's very interesting. But now we have to return to original problem, that we have encountered a step before. Actually, how do we sort vertices? And again, it's kind of not a really trivial problem. We will have to leverage again some maths. So to begin with, it's kind of simple because it's a triangle and we only need effectively two edges, and another edge will just pop out using whether we use counterclockwise or something orientation. Anyway, what I'm saying that if you're given at 3 points that form a triangle, 1, 2, 3 or something, we just have to check two variants. We can connect make one edge 0.1 to 2 and second edge 2 to 3, and then last edge, of course, we will join back. Or we can do it the other way. Still, we take this kind of anchor node 1, and we do it in other order, where these second and third nodes are reversed. And now, obviously, from this image, we see that counterclockwise is kind of proper way for the first case. But how do we do it? Kind of how do we determine it? And well, the observation is such that if we kind of measure the angle between A and B in this order, like a first and second edge, we have to get this angle less than 180 degrees, which of course fails in the second case where it's more than 180. And there are a few expressions which use angles like dot product and cross product. They can be defined via this angle. But in particular, we are interested in this cross product. So there's this kind of expression which is like a signed vector magnitude. In fact, it's okay. It worked. Problem is that magnitudes can be negative. That's what I'm saying, that it's signed. Like it may have negative magnitude. So okay. In particular, because our choice of introduction of kind of this may be additional dimension, that these vectors are coplanar, cross product between our say normal and tangent will have a vector that has only one z component. And that's why this kind of z component, in a sense, it may be positive or negative, and it's enough to calculate this particular z component to understand whether its angle is larger or smaller than 180, just because of the contribution of this term, and that it becomes negative when angle is higher than 180. And so this is kind of mathematical approach, just observation, but then maybe you need some kind of other intuition or something. Well, we can retrieve this z component by just projecting onto z axis, and this expression, okay, first of all, this is expression for z component of cross product, so it's kind of simple. But yeah, but this particular expression also reminds me something of volume of this parallelepiped. Here order naming of vectors are changed, but then again they take a absolute magnitude of this expression. In our case it will not be like sheared like here, because A is just in z direction, but this expression cross product z component will describe the kind of signed volume of this parallelepiped. That's one way of thinking about it. Of course, we are not taking magnitude in this case. And sorting points nodes like counterclockwise, in this case, is kind of ugly implementation, but yeah, I supply points as coordinates and nodes as indices, kind of pointers to these coordinates in list of all nodes, like we did in previous video. And that's what we do. We create two edges. So on image it was A and B or something. We perform this test. The sign of this component. And if this choice kind of is less than 180, then we just return vertices in correct order. If they are not, we just shuffle two nodes. So very simple. And okay, what we did, we understand how to sort them counterclockwise. What we understand is how to measure these projections, and using these two tools, but we can write the whole algorithm. So in this case, we will calculate the projections for each local coordinate system, and if all of them have positive projections, that means that point is inside. Again, completely analogous what we talked about these half planes. The same test. But there are maybe cases when point is outside of triangles. And so, for example, this yellow line is projection for this edge, which is positive. This long, again, is for this coordinate system also positive. But this for this edge with this normal, it will have negative projection, and that would say that if at least one projection is negative, then it is outside of triangle. So first case, if all the projections are positive, we return kind of 1. But then there are some other tests, and also you can see that I employ here a kind of a function to check if projections are greater than tolerance. So we have to actually discuss one issue that may arise. So what if the point is very close to the edge? So maybe you're concerned with some numerical issues, but in reality, how I see it, we don't want such cases where we don't want to create this kind of shallow triangles if the point is very close to the edge. So in case what I propose, maybe we can move this edge, maybe we can kind of split it, but in a sense we can recreate it using this point like this. So it will not be a separate triangle, it will be just split edge. And so we have to detect these particular cases, and we introduce some kind of tolerance. Basically, we want to check, of course, this will be our projection. Kind of it can be positive and negative, and we want to check whether its absolute value is inside of inside of some tolerance band, right? So yeah, that's why that's what I do here. I just take the absolute value, whether it's larger than tolerance or something. So there are cases. So yeah, that's what I say. There may be cases when point will be here, so it will kind of produce two cases with respect to two edges, whether the point is inside this tolerance band. But in reality, you don't even have to have these cases, because if 2 points are nearby, you can check it beforehand and eliminate points that are too close, right? You don't even will have this condition when your point is exactly on top of another node. So that's pretty much what I do. You can kind of follow some logic what I've told you and recreate it if you want. But again, I'm interested only in case when one point is on one edge, and then we can return another kind of signal, which would say we do not split the triangle into 3, we will split the edge into 2, and all the consequences that follow. So yeah, or it is completely outside, we return 0 or whatever, and then there's another complete failure. I've used it for different reasons, and we will not discuss it currently. So yeah, we have just went like a long way to actually understand how to find if a point is inside a triangle. But now it gets much easier, I think. There won't be any math at least. So yeah, again, what our algorithm does, I will make a demo now, but first, yes, we have also understand how to create this particular step of finding point if is inside triangle, and then we will have to perform this kind of splitting, including all the edge cases that we discuss here. And so let's first of all make a demo and try to see like this. First of all, maybe we will just launch this procedure. Let me resize it. So definitely there's some splitting going on, and we see this kind of circle tests, and the outcome is pretty nice. Let's speed up a bit. Also, like an extra, we can like we will be able to remove the external triangles, some internal segments. So yeah, that's how it will look like. You see, it was like splitting, it was doing all the stuff, circumcircle tests, and my actual procedure looks like this. Again, it's absolutely similar to what we discussed in last video in one dimension, but we define some kind of points of buffer which we incrementally insert into our mesh, and we just split. So this is the outer while loop, and this is where we split. But actually we split triangles, and then we have to apply this Delaunay criteria check. And so how it's performed, each time we do a split, there's a separate buffer which contains new triangles, and the algorithm will go through these triangles and determine whether we should flip or not. And that's what I do here. I have this kind of stack which contains these new added triangles that had to be checked. There's a check, and there's this flip. So it's kind of mimicking what is going on here, but also we have some edge cases which are not discussed or described here. But first of all, like, what is the procedure of splitting? So as we have seen again in previous video, splitting is nothing else than we have some kind of data structure that holds information about these triangles, and we just add new triangles into this structure and modify previous entries to include this kind of interrelations. So how do they advise to do it in a book? Spoiler, I don't do it like them, because I have easier kind of method for my particular algorithm. But yeah, what they say, again, they store similarly like in that video. We have this list of entries where each triangle is just indexed in that entry. It has this ID. So yeah, counterclockwise we store the nodes. What they do in a book, they say, okay, first three entries, as in our case, will be pointers to our nodes, and then we have triangle neighbors. So in this case, what they do is they say, okay, this edge HA, if we move three entries to the right, we will get neighbor adjacent to the A. So we go through the opposite edge and we point to this adjacent neighbor, and that's how they store these kind of triangles. And it's true for this B and C. So I guess why they are mainly do it is because there's a way of searching triangles. When we insert a triangle, of course, we have to check whether it's in every triangle, in a sense. Okay, we get the first match, but still, and they propose this method of kind of using our discussed projections to determine the direction across which edge we should move. So they kind of perform this search, and this particular structure, I think, is very useful for this particular application. So what I do in my code, it's a bit augmented. Again, I use not this particular way of searching, but that recursive search and basically this hierarchy tree of how we constructed the mesh, which is kind of fascinating. But so yeah, I do it like similar to in a book, where first three entries are pointers to nodes, but then our neighbors are structured differently. So I say that For example, our node A, it is a kind of beginning of this edge AB. So if you see the edge is held right here, 2 consecutive elements, and the neighbor A is just another triangle that shares that node to our triangle. And then we also have this kind of a child inheritance. So if we split this particular triangle into three new triangles, it will store their indices here. First of all, this approach is not absolutely perfect because we have no way to say from which node we should start when we're storing them. So there are different options, there are different permutations of these 3 nodes, where A can be first, second, or last. So it will be very common that we have to actually search. If we're interested in this node, we will have to search these 3 entries in which position it is, but it's very cheap. And this structure also allows to basically, with smart manipulation and this kind of index switching or going left or right, like 3 indices, you can achieve pretty much everything you need for meshing. There's no need of overcomplicated some kind of data structures, graphs or something, which I actually did previously. I've implemented in Python basically 2 graphs for nodes and for connections between triangles. It's super interesting, exciting for training, but it's not very fast and it's somewhat hard to troubleshoot. So okay, so I would like to give like few observations. Of course, for example, we have this triangle ABC, and then we have this triangle A. It will have nodes ABC, but its neighboring triangle, we have triangles in some other order. It will go counterclockwise, so it will be ADB or DBA or something. But then clearly you know that just by this structure and by that you know that nodes are kind of in opposite directions, you can retrieve all the information. Just okay, let's just consider an example. So during the procedure, we start with one big triangle, we insert this point and form 3 new triangles. One of the triangles, it inherits one edge, and then it creates 2 new edges. When this triangle is created, we do Delaunay test. So we create this circumcircle. And then we have to check if our node opposite to our inserted node, if it's inside the circumcircle. And the question, how do we do it? First of all, we have, like, the end goal, of course, is that we have to retrieve this opposite node, but then we have to find it. And how do we do it in our data structure? So first of all, we start with our node that kind of creates this edge. Then we can understand in our data structure of old triangle which was the neighbor of this old triangle through this edge. So we retrieve index of this triangle, and then again we find this leading edge, but in this case it will be counterclockwise. It will create this particular edge, and we know that if we from position of this node we +1, we will retrieve this opposite node. So this is approximately the procedure of just index kind of shifting, switching, just to retrieve all this information. So it's not hard, you just have to do some observations. And well, again, what we can say, we were talking about data structure, and that splitting is nothing else, just data manipulation. And in fact, yeah, it is it is what it is. Although, as we remember, when we search for a triangle, like in this case, it may return us either if its triangle is inside some triangle or it's on the edge. So we have kind of two cases. In first case, of course, we split it into 3 triangles. In the second case, on the edge, we see that we will have to split it into 4 triangles. Yeah, and all the splitting is nothing else than this kind of insertion, modification of these data entries. First of all, triangle searches. It's way simpler to follow through in example in last video with this recursive search, but here it's absolutely the same plus some kind of edge cases. So again, we start from our first entry. In this case, it will be a giant triangle, which we will not care about anymore. And then we know that basically it doesn't have any children if we inserting first node, and we will split it into 3 new triangles. So anyway, for example, we start from first node, and we know that this giant triangle doesn't have any children, and we will return this particular triangle. If it has children, we will go through all the children, and we will do a triangle test. And then if the point is inside one of the children, we will go on a level deeper until we reach this point where we got the triangle without no children, and then we will return up the stack this particular value. Except our inside triangle test, it may retrieve this kind of, if the point is on edge, and then we will have to return the kind of edge, either nodes or which triangles share this edge. So we'll have to perform this kind of data shuffling. So this kind of split triangle procedure, again, I've said it 3 times, but we just understand that we're inserting one node, create 3 triangles. These 3 triangles each inherit one of the old triangles, parent triangles edges, and 2 new edges are connected to our new inserted points, right? And it's just, we append this kind of data. Again, nodes, neighbors, 3 neighbors will be inherited for all the triangles, and 2 other neighbors are basically new triangles between themselves, neighbors. Yeah. So it becomes kind of a bit more complicated. We can inherit no neighbors and such. This case, when we're splitting edge, yeah, let's of course remember that we just create 4 triangles. So nothing else really changes. And this Delaunay test, again, some extra stuff, but we're interested in this method that we've discussed previously. So where's our Godot? Maybe we can do small demo and try our understanding. So in this case, I will do kind of manual node insertion. So whenever I click it, it will create a node, and we can just try to understand what is going on. So clearly, when I insert node on my pointer, it will split into three triangles. Oh yeah, I had to do manual mode because I want to observe the intermediate steps. So yeah, okay. Again, I insert a node, and then I start iterating. What we can think, okay, it's not obvious, but I've created this node, and it will do a check across this particular edge whether this triangle is inside. So you see it fails this particular test. It will flip. flip is done. Then we can insert another point. Then we will do 3 checks. This edge, so this particular direction, this edge, so this node will be checked, and over here nothing will be checked. So again, we see the circle is huge, and this node red failed. It will split. Will it do something about this? Okay, also it failed this particular test. It will split here. But we had this stack, so once it split these kind of nodes, it added them to stack, and they had to be processed. And what we see that for this triangle, this node is too far away, this kind of small, it's too small. For this large triangle, so across this diagonal, this node is still outside. So what it only detected, this kind of nodes, these two new like flipped triangles did not fail, but this particular is still considered failed, and it flipped. And then again, these two nodes are in the buffer, in a stack, and they will be checked. And apparently they are okay. So yeah, and then you can kind of mindlessly add these nodes, and in the end we will get some kind of mesh that's pretty uniform, which is ideal for FEM simulations. With kind of some magic, again, we can try to do, we can kind of strip the external triangles, we can strip internal triangles. These are just extras. But yeah, that's everything that I wanted to cover in this video. And in the next video, I don't know what I will still do. I think maybe I will do transient 1D simulations, or I will show you how to implement actually two-dimensional FEM. So let's see what I have. Just a second. Nothing will break. Something broke. Anyway, we will see it in a next video, and thanks for watching.